Hi, welcome to World Unknown. Today we are going to explain about quantum time, quantum gravity, and imaginary time. Come on, let's get started. In the first half of the 20th century, a whole new theory of physics was developed, which has superseded everything we know about classical physics, and even the theory of relativity, which is still a classical model at heart. Quantum theory or quantum mechanics is now recognized as the most correct and accurate model of the universe, particularly at subatomic scales, although for large objects classical Newtonian and relativistic physics work adequately. If the concepts and predictions of relativity, see the section on relativistic time. Quanta. One of the implications of quantum mechanics is that certain aspects and properties of the universe are quantized, that is, they are composed of discrete, indivisible packets or quanta. For instance, the electrons orbiting an atom are found in specific fixed orbits and do not slide nearer or further from the nucleus as their energy levels change, but jump from one discrete quantum state to another. Even light, which we know to be a type of electromagnetic radiation which moves in waves, is also composed of quanta or particles of light called photons, so that light has aspects of both waves and particles. And sometimes it behaves like a wave and sometimes it behaved like a particle. Wave-particle duality. It should be noted that our current knowledge of physics remains incomplete, and, according to some theories that look to combine quantum mechanics and gravity into a single theory of everything, often referred to as quantum gravity. See below, there is a possibility that time could in fact be quantized. A hypothetical Granon unit for a proposed discrete quantum of time has been proposed, although it is not clear just how long a Granon should be. Copenhagen interpretation. One of the main tenets of quantum theory is that the position of a particle is described by a wave function, which provides the probabilities of finding the particle at any number of different places, or superpositions. It is only when the particle is observed, and the wave function collapses, that the particle is definitively located in one particular place or another. So, in quantum theory, unlike in classical physics, there is a difference between what we see and what actually exists. In fact, the very act of observation affects the observed particle. Another aspect of quantum theory is the uncertainty principle, which says that the values of certain pairs of variables, such as a particle's location and its speed or momentum, cannot both be known exactly, so that the more precisely one variable is known, the less precisely the other can be known. This is reflected in the probabilistic approach of quantum mechanics, something very foreign to the deterministic and certain nature of classical physics. This view of quantum mechanics, developed by two of the originators of quantum theory, Niels Bohr and Werner Heisenberg, is sometimes referred to the Copenhagen interpretation of quantum mechanics. Because the collapse of the wave function cannot be undone, and because all the information associated with the initial possible positions of the particle contained in the wave function is essentially lost as soon as it is observed and collapsed, the process is considered to be time irreversible, which has implications for the so-called arrow of time, the one-way direction of time that we observe in daily life. See the section on the arrow of time. Many worlds interpretation. The Copenhagen interpretation of quantum mechanics, mentioned above, is not, however, the only way of looking at it. Frustrated by the apparent failure of the Copenhagen interpretation to deal with questions like what counts as an observation, and what is the dividing line between the microscopic quantum world and the macroscopic classical world, other alternative viewpoints have been suggested. One of the leading alternatives is the many worlds interpretation, first put forward by Hugh Everett III back in the late 1950s. According to the many worlds view, there is no difference between a particle or system before and after it has been observed, and no separate way of evolving. In fact, The observer himself is a quantum system, which interacts with other quantum systems, with different possible versions seeing the particle or object in different positions, for example. These different versions exist concurrently in different alternative or parallel universes. Thus, each time quantum systems interact with each other, the wave function does not collapse but actually splits into alternative versions of reality, all of which are equally real. This view has the advantage of conserving all the information from wave functions so that each individual universe is completely deterministic, and the wave function can be evolved forwards and backwards. Under this interpretation, quantum mechanics is therefore not the underlying reason for the arrow of time. Quantum gravity. Quantum gravity, or the quantum theory of gravity, refers to various attempts to combine our two best models of the physics of the universe, quantum mechanics and general relativity, into a workable whole. It looks to describe the force of gravity according to the principles of quantum mechanics, and represents an essential step towards the holy grail of physics, a so-called theory of everything. Quantum theory and relativity, while coexisting happily in most respects, appear to be fundamentally incompatible at unapproachable events like the singularities in black holes and the Big Bang itself, and it is believed by many that some synthesis of the two theories is essential in acquiring a real handle on the fundamental nature of time itself. Many different approaches to the riddle of quantum gravity have been proposed over the years, ranging from string theory and superstring theory to M-theory and brane theory, supergravity, loop quantum gravity, etc. This is the cutting edge of modern physics, and if a breakthrough were to occur it would likely be as revolutionary and paradigm-breaking as relativity was in 1905, and could completely change our understanding of time. Imaginary time. While looking to connect quantum field theory with statistical mechanics, theoretical physicist Stephen Hawking introduced a concept he called imaginary time. Although rather difficult to visualize, imaginary time is not imaginary in the sense of being unreal or made up. Rather, it bears a similar relationship to normal physical time as the imaginary number scale does to the real numbers in the complex plane, and can perhaps best be portrayed as an axis running perpendicular to that of regular time. It provides a way of looking at the time dimension as if it were a dimension of space, so that it is possible to move forwards and backwards along it, just as one can move right and left or up and down in space. Despite its rather abstract and counterintuitive nature, the usefulness of imaginary time arises in its ability to help mathematically to smooth out gravitational singularities in models of the universe. Normally, singularities, like those at the center of black holes, or the Big Bang itself, pose a problem for physicists, because they are areas where the known physical laws just do not apply. When visualized in imaginary time, however, the singularity is removed and the Big Bang functions like any other point in space-time. Functions like any. If you liked this video, please hit the like button. If you want to see more videos, hit the subscribe button. And if you have something to say, please leave a comment. Thanks for watching this video.